לא. מה היית רוצה שיוכיחו לך? מה חסר לך?
בא ואומר פה מלא טענות. אם ככה אז ככה, אם ככה אז ככה.
תלוי. כמה חשוב לך שיוכיחו לך דברים?
אני לא מאמין.
מה נבדוק? תראה,
מתחבר.
מה שאמרנו זה על...
תמיד הדברים הפשוטים האלה הם הכי פשוטים.
כן, בדיוק דיברתי עם איזה חבר שכזה טריאתלוני, אמר לי, אתה תגיד, זה אפליקיישן שלו. אני לא יודע, בשביל הכיף, לא בשביל הכיף. בסדר, כי אם אתה אומר של הבריאות, זה כנראה יותר לא בריא מבריא. ואז זה ככה.
אני רואה שאפשר להוכיח את הדברים האלה, אבל זה לא מספיק חשוב. זה לא מספיק חשוב. לפחות אינטואיטיבית אני רואה שאפשר. Okay. Is this everyone? We are missing Carmel and Ronnie and not sure who else. Okay. Okay, today we are going to finish our survey of bifurcations in 2 dimensions. And then we are going to go into 3D systems, and specifically nonlinear, because it's more interesting. And introduce the topic of chaos in nonlinear systems. Right, so as for the bifurcations, last week we saw the bifurcations that are just extensions of the bifurcations in 1D, saddle node, transcritical, and pitchfork bifurcations that occur on 1 dimension actually, which could be the x or y dimension or some linear combination of x and y. But the idea is that the bifurcation parameter controls 1 dimension. I mean, there is one bifurcation parameter whose change can give us a 1D bifurcation. And then the 2D behavior is just a regular, either stable or unstable fixed point, to be half stable maybe, but it doesn't care about bifurcation in the first dimension. So now we're going to look at bifurcations that are special to the 2D systems. I guess they can happen also in 3D systems, but they will involve limit cycles. And I'll see how we go. I'm not sure I'll have time to show all of them, but the most important one is called the Hopf bifurcation. And what happens in the Hopf bifurcation is that we have a fixed point that loses its stability while opening a stable limit cycle around it. Can also be the opposite, right? An unstable fixed point gaining stability while an unstable limit cycle opens around it. And of course, at the bifurcation, the limit cycle is very, very small, very, very close to the fixed point. And as the bifurcation parameters is changed, then the limit cycle diverges from the fixed point. And a way to, well, conceptualize this is to think of what happens to a fixed point when it loses stability. So we know that a fixed point is stable if both its eigenvalues are stable. So we could make this cartoon where a stable fixed point, for example, would have two real eigenvalues. Usually we find them according to tau over 2 plus minus some square root over 2. So basically, two stable real eigenvalues. This would be the imaginary axis. And to lose stability, we need to have one or two of them cross. So they're both negative, and to lose stability, we need to have one or two of them cross into the positive values. Maybe I switched the positive and negative before, but they should be negative for us to have stability. Stable, and then if some bifurcation parameter will separate them from one another, then one of them might lose its stability, or maybe the two of them will shift together with tau. The two of them will shift, and the fixed point will be completely unstable. And what happens in a Hopf bifurcation is different than this. I'll make a similar cartoon. And here we are dealing with spirals. So spirals would have two conjugate eigenvalues. So this will be a stable spiral. And the two conjugate eigenvalues would both shift with a change in the bifurcation parameter. Let's say it's called mu. And they will both cross this imaginary axis at the same time. So the spiral would immediately become an unstable spiral. And from this situation, for example, we would go into this situation where the unstable spiral, the projector is going out of it, and converge into the limit cycle.
We never saw something with the real part of the two eigenvalues equals 0. Like when they cross,
With the real
when the two real parts of the eigenvalues are 0.
are 0.
We never saw. We saw only when one eigenvalue is 0, and what happens when they cross?
Okay, so exactly when they cross, Um, so exactly when they cross, you would get, I'm not sure that in all cases, but you're supposed to get closed orbits. An infinite, the situation of infinitely many closed orbits. Only in a nonlinear system, this might be true only for the close vicinity of the fixed point. So it becomes a kind of neutral stability in between the stable and unstable. Neutral stability with closed orbits around it, and then the unstable. Excuse me? Yeah. So the closed orbits are like limit cycles, except that they're not isolated. Or maybe I have something that I wrote over. Yeah. Okay. Okay, so the situation, I was going to get to it later, but the situation where you pass here through the closed orbits, this is called a degenerate Hopf bifurcation. So in fact, I'm not sure what happens in the other cases of the non-degenerate Hopf bifurcation. Okay. So with the Hopf bifurcation, we're not going to give an analytical treatment. We're just going to introduce it, and in your exercise, you will see it happening in a numerical simulation, which is very nice. And the way we draw it on the bifurcation diagram is we would have some stable branch, some stable fixed point, and at the bifurcation point, this spiral would turn unstable, and we would have a limit cycle opening. And to distinguish this from the pitchfork bifurcation, it's customary to do this drawing of a cycle, okay, to show that on the x-axis these are not in fact fixed points, but it's a cycle going within this amplitude. Okay. No, so it doesn't jump. It's a cycle, but here you don't have the y dimension. I mean, you could add it, right? And then this would be a kind of sleeve, three-dimensional in the x, y, and mu. Okay. But usually the bifurcation diagram it looks only like this. Okay. Yeah. What am I drawing? This is the bifurcation diagram. The curves on the bifurcation diagrams are the fixed points.
But what you draw a function of x is fixed point and y still.
Yeah, so we are in 2D, but I can draw the bifurcation diagram for the x-coordinate of the fixed points and for the y-coordinate of the fixed points separately. I could do it as curves in 3D space, like I showed Chagai just now. Right, so
X that has a fixed point here has
a y.
a y that together forms.
Yeah, so usually it would be x versus the bifurcation parameter, and on a separate diagram it would be y.
Okay, and then what happens at the bifurcation
So this is the stable spiral. This is the unstable spiral. The dashed line is an unstable fixed point. And here, these are two curves marking the boundaries of the limit cycle. Okay, so our situation is that we have an unstable fixed point and a stable limit cycle, and let's say that mu is getting bigger. So for different values of mu, I will have a different amplitude for the limit cycle. Okay? And this is what I'm showing here on a projection, a sort of projection. So these cycles that I drew, they're not, it's just an illustration. I would, to make it more strictly accurate, it would have to be something like this. Right. But it's just an illustration.
So these are the radius kind of the
Yeah.
cycles?
Okay, so this situation would be a supercritical Hope bifurcation. And of course, the stabilities could be opposite, right? You could have also x versus mu. This would still be a supercritical Hope bifurcation. And then you would have the subcritical, where it's just the opposite situation. This is, in fact, often seen in neural networks or models of neurons, where you might have a region where the network fires constantly, fires spontaneously, versus some parameter mu, which is, for example, an external input. And then when the external input is very big, you actually go into a region of firing. In the neural networks, it looks different. It usually looks like this. So this would be the subcritical Hope bifurcation, and this would be, for example, external input. And this would be some parameter that is like could be a firing rate, or some other parameter like postsynaptic current. And here you would have the network would be quiescent. It will have a spontaneous firing rate of almost 0. At one point, it's actually at this point, the quiescent fixed point is unstable, and there is a limit cycle opening with a bifurcation that we didn't see yet. And then you would have this bursting region, and if the external input is very big, you would have the tonic firing. In your homework, you have a model of a neuron with a Hope bifurcation. But I think it's interesting that actually the tonic firing comes after the region of bursting. It's pretty typical for these systems. Um, okay. So one nice analogy for what happens in the Hope bifurcation that might help understand what's happening here is the analogy of a damped oscillator. So we saw oscillators when we talked about when we started talking about the limit cycles. So you could think of a damped oscillator with some parameter mu, where for mu smaller than 1, there is dampening, like we saw in the system in the van der Pol oscillator, and when mu is taken to be larger and larger, this is not in fact it doesn't act to dampen the oscillation, but to increase it. Or maybe if we actually started from some specific value, which could have been a fixed point, we cannot stay there because it's unstable, and we have increase into stable oscillations. So this will be for the mu larger than 1, or some other critical value. Okay, so like I said, the size of the limit cycle grows as we leave the bifurcation point. And near the bifurcation point, the amplitude of the limit cycle grows linearly. Grows like the square root. Grows like the square root of the distance on the bifurcation parameters axis, and similar to what we saw with the saddle node, that the points separated according to a square root relation. And the period of the limit cycle close to the bifurcation point scales inversely with the imaginary part of the eigenvalues, with an addition that is on the order of the distance on the bifurcation axis. So this is very crude, in fact, and the dependence on the imaginary part is actually a little more complicated in practice. But this is like
What is T again?
a rule of thumb. T is a period.
Period.
It's 1 over S.
And it's again also only to surround the fixed point?
Yeah. Okay. So, excuse me? Why is this a period? Because the
time takes to go around?
yeah. Why is this a period? Because if you remember, the imaginary part of the eigenvalue goes into the cosine and sine, or actually in the argument of the. Okay. Well, if the imaginary part is A plus BI, then we know that around the fixed point x of t, it goes as e to the lambda t, e to the at. This will be a decay or a growth. There. This separates into the cosine with bt. And so this is the imaginary part. So bt would be the omega that you usually write in the cosine. Right? And to translate from time to periods, you have 2 pi. Okay, so this is the Hope bifurcation. Like I said, I'm only telling you about it, and I'll let you see it for yourself in the numerical simulation that you are going to implement. And it's also because there's not much to do here. I mean, at this point, we are more. We will deal with these things more in using numerical methods. Okay, with the limit cycles, you don't really have expressions for the trajectory of the limit cycle. So we just see it in numerical simulations. I'm going to move now into types of bifurcations called global bifurcations of cycles.
Bob,
Yes.
why when you do the lower one on the left,
This one?
yeah, you switch everything to stable, you put unstable, everything unstable, you use
Yeah.
stable. Besides the limit cycle. Stable.
Yes. Well,
Why is that?
just for illustration purposes.
So it should be dashed.
Yeah. Yeah. It should be dashed. It's only. I didn't want to confuse you with all these dashes here. Yeah. It's not too bad. This way. Okay, so the global bifurcations are bifurcations that they're global in contrast to local bifurcations. These bifurcations don't happen necessarily around the vicinity, at the vicinity of the fixed point. Okay, so for example, there were 3 I wanted to show you, but we'll see if we do all 3 of them.
Can you explain again the meaning of what sense is it global?
You'll see in the example. Okay. So the first one will be a saddle node bifurcation of cycles. And what we have with the bifurcation of cycles of this type is limit cycles, an unstable and a stable limit cycle converging and disappearing, annihilating each other. So for example, we have a system, for simplicity, we are looking at the polar coordinates. Okay, so here we have fixed points in R equals 0. And R squared equals um, so let's do this. Okay. So if we draw the phase portraits for R, when mu is very small, we will get only one fixed point. So this means we won't have a square root here. We won't have a real solution for this. When mu is equal to mu c, then in R we would have a saddle node bifurcation, a half stable fixed point, and you already know that if mu is greater than mu c, we will have these fixed points separate. And this situation is just it would just be the situation of a spiral at the origin. Here, the spiral at the origin is still stable, and around it we have a half-stable limit cycle, which means that everything starting within the limit cycle will descend into the fixed point, and everything starting outside the limit cycle will eventually converge to the limit cycle, but it cannot go further in. Excuse me? Yeah. If you start exactly on it, then you stay there.
Can you explain again this case?
The half-stable limit cycle?
Yeah. It looks like a spiral.
Inside there is a spiral. So
And this is for R equals 0?
for mu equals mu c. Yeah, you descend into R equals 0. For anything within the limit cycle. If you start exactly on the limit cycle, you stay there. But if you start outside the limit cycle, you go into the limit cycle. So like a half-stable fixed point, you either go into the limit cycle or out of it, depending on your initial condition.
But this is a 2D, so can't you cross the other side of the fixed point when you start with the digging of R? So you get to the limit cycle, but it's not. But you will cross it.
And no,
Why not?
because once
It's looking like it's like 1 maybe, because when you one
here,
equation for R.
yeah, because there is only it's polar coordinates. You only consider the distance from the origin, the radial distance. So in this system, this value of R would always be a half-stable fixed point, no matter where you reach it.
Yeah, I'm just saying usually on 2D systems,
Yeah.
you can put different things like exponential, like decay to the point. You can also cross to the other side, right?
Say again?
In a 2D system,
Yeah.
you can cross the fixed point to the other side. You don't just exponentially decay to it and stop when you reach it. Let's say in other.
So
This is what happens in 2D systems usually.
it depends what happens on the second dimension. Yeah.
Okay, so this is like a particular case when nothing interesting happens.
Yeah.
So you don't.
Yeah. This is a symmetrical case. Mm-hmm. The question was whether this is not a partial representation where on one dimension, say on the x dimension, you would get to this value and it acts as half stable, and on the another dimension, you would be able to kind of go around it and then descend into here. But our case is symmetrical. It has polar coordinates, so it has radial symmetry. Okay, and the last case is this one, where you have a fixed point, an unstable limit cycle, and a stable limit cycle outside. And just remember that if you have concentric limit cycles, they should always switch stability. Just like the fixed points on the one dimension. Yeah. Well, because there is radial symmetry here. Okay, this is just a simple system on which I can give an example. So the idea behind the term global bifurcation is that this bifurcation did not occur near a fixed point. It occurred in a wide area of the phase plane. Okay, it occurred around this half-stable limit cycle. This is why it's called global. Okay, can I move the board to cover this? I will show one other type of global bifurcation. Or yeah, if we have time, I'll show the third. Okay, the next type is called a homoclinic bifurcation. Yeah. Yeah.
I didn't understand why global bifurcation is important to understand.
It's not so important to understand, but it's just a term. It's just a term, and it relates to the fact that up to now we had, let's say, one fixed point losing stability, and okay, in the saddle node we have two fixed points converging at one place and disappearing. Okay, and the transcritical has two fixed points meeting and switching their stability and then going apart. And the pitchfork is similar. It's one fixed point suddenly turning into three fixed points. It all happens at one point in the phase plane. So basically, and you can linearize in this point and see the local behavior that is approximately linear. And here, the bifurcation does not happen in a point. It happens to the limit cycle. So you could have a phase plane where the limit cycle is not so nice like we saw before. Okay? And okay, so these two limit cycles will become more and more similar to each other and finally disappear. And this thing happens along this whole curve on the phase plane, not in a single point. So it's not something you can linearize at this point. Accordingly, the methods to find this and treat this are numerical. Okay, the homoclinic bifurcation occurs when we have a saddle point And there is also a limit cycle where the saddle is outside the limit cycle. Of course, if you have a stable limit cycle, you should have a fixed point inside it, an unstable fixed point, unless you have concentric limit cycles. And in this bifurcation, the limit cycle merges, kind of swallows the saddle, and becomes what is called a homoclinic orbit. Of the saddle. So a homoclinic orbit occurs when the when the unstable manifold actually is the same as the stable manifold. Okay.
And there were two fixed points?
Yeah, the one in the middle, I don't think it should, I don't remember if it should be, yeah, it stays there. So
And the saddle
it's not
stays
affected.
saddle or should?
The saddle stays a saddle, it just becomes a very special saddle. Okay?
So the line like separating between them is long. Like, can you draw the? If I start on this orbit, just
If you start
on the after
here,
on this orbit. Yeah. How do I go? How does it go?
you go to the saddle.
Yeah, and continue the circle.
No, you cannot. Because if you remember, you never actually reach the saddle. It's an exponential decay.
There's no limit cycle.
This is not a real limit. Yeah. So it's called an orbit. It's not in fact a closed orbit because you cannot go round and round.
If I start on the small one.
If you start, say again.
On the small one.
Which one is small?
This is a fixed point. I thought it's another. No. Orbit.
This is a fixed point. Yeah. In the 2D, it's the same notation for a saddle and an unstable fixed point. Unstable.
Can the cycle go then beyond the second fixed point?
Can the cycle be here, like close here?
Go all the way around both of them, like later. First of all, it's just around the fixed point to the right, and then it.
No, because it's kind of tethered here. It's anchored to the saddle. The saddle must have its unstable, stable manifolds, and it's yeah. So it can. This is actually what I think. This is what happens here, if I'm not mistaken, with the limit cycle. Okay, not exactly, but for me, when I was dealing with such a model, it was puzzling that what happens here. It looks like a saddle node, but I know that there is a limit cycle beyond here. In this type of bifurcations, where a limit cycle suddenly is cancelled, this is what happens when you see a limit cycle occurring for part of the bifurcation axis, but not closing, like in the Hope bifurcation, then this is the type of things that you will have. Or either it meets with, of course, with an unstable limit cycle, like we saw before, with the bifurcation of cycles. Okay. I want to show an example. Now let's turn the projector on. Okay, while we wait for the projector, do you see it turning on? Yeah. Right? Okay, so while we wait for the projector, I will just mention the other type of bifurcation, It's called an infinite period bifurcation. And here, what happens is you have a limit cycle and as you change some bifurcation parameter, then you get two okay, at the critical point you get an unstable fixed point on the limit cycle. Okay, this is at mu c. And as you keep changing the bifurcation parameter, you get this separating into two fixed points. So, like this. And this is the infinite period, okay? You never complete a full cycle because you approach exponentially the half-stable fixed point. Okay, even if you started very close here, you will never actually meet the fixed point, and you will be trapped. And then from here on, it's no longer a limit cycle. This is actually because the term is interesting. This will be called a heteroclinic orbit. So, or trajectory.
Shouldn't the upper orbit, the point,
Say again?
the upper orbit shouldn't like still also have a point? Upper one, no?
This one? This one?
Yeah, shouldn't be filled? Like,
Well, if I would like to actually draw a saddle this way, then I guess I would need to do something like this.
but this one is not a saddle.
Right. Yeah, so this one is a saddle. This is still a saddle. Okay. This one, if this was a limit cycle. Yeah, so I only know this from the example of the infinite period bifurcation. So this is similar to what we saw when we did the 2D example of the saddle node bifurcation, where we had an unstable fixed point and then it became a ghost. Okay, we had a saddle and a node converging. Basically, this is what happens here. This is a saddle node bifurcation occurring on the orbit.
But this is an unstable fixed point or a saddle?
This is a saddle, because remember that everything goes into the limit cycle. So on the limit cycle, things go out of it, but inside and outside of the limit cycle, things go into it. And this is a stable fixed point. So a saddle and a node, and they converge here in a saddle node bifurcation with a half-stable fixed point. And an orbit like this that connects one fixed point to the other is called a heteroclinic orbit. In contrast to the homoclinic orbit that connected one fixed point to itself. Can only happen in a saddle, obviously. Or with this one, I guess.
Can we maybe take a break before we continue?
Yeah, I'll prepare the demonstration, and then we will start with the demonstration. כן. לגבי התרגיל הרביעי. אז אחרי השיעור. כן, אני צריך עכשיו לנסות כמה דברים.
כל מה שמעניין במסה שני המדים,
כן.
שאתה חוצה את הנקודת שבט, יש לך אוסילציה.
זהו, שאתה לא חוצה אותה.
אתה... יש לך אוסילציה.
כן.
נקודת שיווי משקל. אוסילציה, נקודת שיווי משקל.
כן, אבל כשאתה מצייר את זה על הפייס פליין, אתה לא חוצה אותה. אתה... הרי... למה?
אתה הופך משוואה מסדר שני
לסדר ראשון. לא, לשתי משוואות מסדר ראשון, כן.
אז אתה תצייר עכשיו משהו כמו x דוט של x ו-y דוט של y איכשהו ביחד.
כן, נכון. זה הוקטורים שאנחנו מציירים על הדו-מימד.
אז איפה, אני רוצה להגיד, אני לא מבין איפה אנחנו רואים שאנחנו חוצים נקודות, כי זה מה שקורה, במשוואה דו-ממדית. כל פעם פה הדוגמה אנחנו פשוט משוואה דו-ממדית, ופשוט נצטרכת למד אחד, אבל כאילו הם בלתי תלויים. זה לא ממש מעניין.
בדוגמאות של הביפורקציות?
בכלל, גם שבוע שעבר, כאילו אנחנו תמיד דואחים לנקודה יציבה, דואחים אקספוננציאלית, ונקודה לא יציבה, אנחנו מתקדמים אקספוננציאלית.
נכון.
אבל זה לא מה שמעניין בדו-ממד.
אוקיי.
סתם חד-ממד, פעמיים.
אבל מה שמעניין בדו-ממד היה לנו, עוד לפני הביפורקציות ראינו את זה, ראינו שיש או ספירלה או לימיט סייקל, ואז על הפייס פליין, שיכול להיות נגיד מהירות כנגד מקום, אז אתה עושה את זה, אבל אם אתה תסתכל רק על המקום, אז אתה באמת חוצה אותה. ואם תסתכל רק על המהירות, אז גם אתה חוצה את... על כל מימד אתה אכן חוצה, כלומר אם תצייר כמו שאמרת, x דוט מול x, אתה תראה שאתה חוצה את ה... פה בביפורקציות. זה כי... אוקיי, כי בהתחלה התעסקנו רק ב-x דוט מול x חד מימד, אין אוסילציות. בשבוע שעבר הסתכלנו על Saddle Node Bifurcation, ששם הנקודות לא הנחנו שהן ספירלות. אז בגלל זה הדעיכה הייתה ישר לנקודת השבט. אבל אם היא ספירלה, זה לא קורה, כי אם אתה זוכר, כשציירנו את התא והדטרמיננטה, אז סאדל ונוד ייפגשו, כאילו, הסאדל לא ייפגש עם ספירלה, אני חושב. מה שיש לנו זה ספירלות, כאילו ספירלה שהופכת ל...
אני רוצה שנתח מערכת כזאת, כמו משהו כזאת.
כפול 4 ריבוע, 4 ריבוע מינוס 1.
ש-x חיובי.
כן. ואז מה תעשה? x דוט שווה y, אז y דוט שווה מינוס kx.
ואז לראות עכשיו איך זה. כי פה יש השאלה של נקודת שיווי משקל. איך אני יכול לראות את זה עכשיו בדינמיקה?
x דוט שווה y, אז יש לנו y שווה 0, זה נוקלינה, x שווה 0 זה נוקלינה, j שווה 0, 1, מינוס 1, 0, תau שווה
המהירות שהוא הולך לכיוון.
אני צודק פה?
קיצר,
כן.
בדינמיקה של
כן.
R,
R שווה 0,
R שווה 1 זה
J כן, J ב...
כלומר R מתכנס
רגע, למרות רק שהוא מינוס K. אתה גוזר.
מינוס K.
בעקבות הסיבה. לכן
זה
R
המינוס
מתכנס ל-1.
D שווה K.
כלומר, ה-D מתכנס
תא שווה 0, D שווה K. איפה הציור שלי? זה פה.
משוואה לסטה,
אוקיי.
זה ה-closed orbit.
לעומת כזה.
שתלוי בנקודת ההתחלה שלך, מה האוסילציה. מה
Closed Orbit זה limit cycle?
זה לא, בהגדרה זה שונה מלימיט סייקל, אבל closed orbit זה מה שקורה באוסילטור הזה, שאיפה שאתה מותח את הקפיץ, זאת האמפליטודה שתהיה עד אינסוף. אז ה-closed orbit, כאילו יש לך אינסוף מסלולים, כל תנאי התחלה הוא מכתיב מסלול מעגלי. סביב, ואז אם אתה מסתכל רק על X, אז אתה רואה אוסילציות כאלה סינוסוידליות ב-X.
ואז יוצא שתטא תג, או הנגזרת בזמן, היא מינוס 1.
אם הייתי מוסיף פריקסון פלוס C,
כן.
הייתי גם רואה דעיכה.
כן, אז היית רואה ספירלה.
המשוואה
כן.
מקבלת למדה
כן.
X תג שווה למינוס X, לא מינוס X, מינוס 1. כלומר זה אומר שיש איזו מהירות קבועה במינוס 1. העובדה שזה מינוס 1, זה אומר שזה הולך ככה. שתטא הולך לכיוון המינוס. כלומר אם היא נמצאת ב-2, היא הולכת לכיוון 0. אז זה clockwise. ואיפה שאמרת לי על ה... למרות שזה לא נמצא. זה לא כזה משנה.
כן.
לשאול לגבי התמהיל, האם אפשר להוכיח בשעה הרביעית שאין לי לימיט סייקל מכיוון שהאינדקסים מבקרים את השני? נגיד 1 זה מינוס 0,
כן.
ואז אין לי פיקס פוינט.
היית יכולה להגיד שאין לימיט סייקל שמקיף רק את שתי הנקודות האלה.
כאילו, עוד 4 טעם ביחד.
סליחה?
או נגיד, אפשר 4 נקודות במקרה שלו.
או אם הסכום של 4 נקודות הוא לא פלוס 1, אז זה לימיט סייקל שמקיף את 4 ביחד. אבל אם יש נקודה שהיא פלוס 1, או נקודה שהיא פלוס 1, יש שתי נקודות פלוס 1 ואחת מינוס 1.
בנפרד, כן, כל אחד בעצמו יכול
יש
להיות.
כל מיני אפשרויות שיתנו לך פלוס 1
נכון.
בתוך הלימיט סייקל. אז את צריכה להגיד על כל אפשרות כזאת למה היא לא אפשרית.
אני רוצה להגיד למה כל אחד בנפרד?
למה כל אחת שהיא פלוס 1, אז כן.
לא על כל המערכת.
לא, את צריכה להגיד, לא יכול להיות לימיט סייקל שמקיף את כל הנקודות בגלל שהאינדקסים שלהם לא מסתכמים
נכון, לא צריכה להתייחס לכל נקודה, האם היא לימיט סייקל כן או לא. נפרד.
הנקודות שהאינדקס שלהם פלוס 1, אז כן, כי בתיאוריה יכול להיות לימיט סייקל שמקיף רק את הנקודה הזאת שהיא פלוס 1.
כן, אבל השאלה התייחסה לכל המערכת.
לא, השאלה התייחסה לכל המערכת במובן של האם במערכת הזאת יש לימיט סייקל. ואז את מנסה להגיד, טוב, אז פה סביב הנקודה הזאת לא יכול להיות, סביב הנקודה הזאת לא יכול להיות. עכשיו, יש לי 3 נקודות שמסתכמות באחד, אז האם יכול להיות שיש לימיט סייקל סביב שלושתן? וככה כל האינדקסים אומרים לך איפה האפשרויות ללימיט סייקל. סביב זה, סביב זה, סביב הצירוף הזה של נקודות, וזה הרעיון.
ורציתי לשאול, זה משהו שהתחלתי בשעה 5, בכלליות אבל גם, כי יש לי בעצם איזשהו שורש של משהו שלי למשל, ואני יכולה לקרוא לזה נגיד 5i, נכון?
כן.
ואז אני יכולה להגיד לך את הדלטה, זאת אומרת את
דטרמיננטה והטרייס, כן.
כן, אז צריך לעשות דלטה ריבוע חלקי 4 פחות דלטה, ואז אם הדבר הזה נגיד כביכול חיובי, ואני מתייחסת לזה די בתור נראה. כאילו אני חייבת את זה בכל מקרה, אם נגיד אצלי בכל מקרה שדטרמיננטה שלי בכל מקרה שלי,
כן.
אז אני בכל מקרה נכנסת לסדר, לא משנה אם יש לי
נכון, כן.
אני לא משתתף בעיפרון.
ואם אצלי הפוך, יש לי...
דטרמיננטה חיובית.
כן, זה מספרים מורכבים.
את מסתכלת...
לא, פה טעיתי בכיוונים.
כאילו...
הדטרמיננטה היא מורכבת.
ריבוע חלקי 4 פחות דלתה, כל זה חיובי, אבל מספרים עצמם מורכבים. יכול להיות מצב כזה?
כן, אני חושב שכן. את אומרת ש... רגע, הערכים העצמיים הם ממשיים?
טוב, כאילו...
אמרת טרייס ועוד שורש טרייס בריבוע מיוצר ב...
טוב, לא ממשיים.
הערכים העצמיים לא ממשיים, כן?
שזה מצב שנגיד...
אם הערכים העצמיים לא ממשיים, אז את בכל מקרה נמצאת באזור הזה.
כן, אבל אני לא יכולה לקטלג את זה, כי אני חושבת ל-i בתור משהו כאילו חיובי או שלי, או כאילו 5i ועוד 10i כביכול, 15i, כביכול יכולה להגיד שזה חיובי. אם אני חושבת לציר כאילו imaginary y ו-imaginary x.
אין imaginary y ו-x, x והם רק ממשיים, ואת צריכה להסתכל על החלק הממשי של הערכים העצמיים. אם הערכים העצמיים מרוכבים, אז את צריכה להסתכל על החלק הממשי בשביל לקבוע את היציבות. ואם אין חלק ממשי, אז זה אומר שאת נמצאת פה, טרייס שווה 0. נמצאת על הקו הזה, ואת כנראה במקרה של closed orbit.
אוקיי, אבל יכול להיות מצב ש... אבל איך אני בעצם אומרת שזה חיובי בגלל שנגיד את זה 15i, אני אומרת ש-15i זה חיובי ו...
לא. אם יצא ל-15i, אז התא הוא 0.
הערך הממשי.
הערך הממשי הוא 0. real, זה אין לי פה. real, לא imaginary lambda, real lambda הוא 0, ואז היציבות היא סוג של ניטרלית, כמו בנקודה שבתוך ה-closed orbit. יכולה לזוז ממנה ואת תהיה ב-closed orbit.
שאלות לגבי התרגיל.
כן.
קודם כל, כשמדברים על אינדקסים, שאני מדברת על אינדקס של סאדל נוד או של אנדסטייבל נוד, אני יכולה להשתמש בזה פשוט כנתון שזה האינדקס, אני צריכה להתחיל להסביר מחדש. אוקיי, עכשיו בשאלה אחת שאתה מבקש למצוא את האמפליטודה של הסייקל, הכוונה לרדיוס שלו?
כן.
כן, אוקיי.
תכתבי, אם את מדברת על רדיוס או על קוטר.
2 פאי חלקי
כן.
מחזור כמה שאלת רק על כיוון, לא?
שאלתי גם על מחזור.
מה ששאלתי אותך באינטרנט, נכון שזה לא יפה, אבל זה הספירלה, כן?
לא, אתה צדקת.
כן, אוקיי. אם אני מפעיל פה...
הרמז שלי בעצם נתן לכם אפשרות שזה יהיה טריוויאלי, כן.
פשוט להסביר את זה, אז הסברתי במילים.
אין בעיה שתסביר במילים, אתה אמור להסביר פה במילים.
כן, כי אם אתה מתחיל מפה, אז לפי מה שקורה בדינמיקה, אתה הולך.
כן, אתה אומר...
ואתה חייב לחזור גם לנקודה שהיא לא פה. אם אתה מתחיל בחץ הזה, ואתה סיבוב, אז אתה לא יכול לחזור למשל לפה, כי אז הבא בתור...
יחתך.
האמת שהוא גם יכול.
אבל אתה יודע זאת מושכת את כל המסלולים.
הוא יחתך כי הוא יקיף אותו.
כן.
אולי לא.
אתה אומר שאתה חייב להגיע לפה בסוף, נכון?
מה שאני... גם לפי הדינמיקה, באמת אפשר לראות שאפשר...
כן.
כל העניין להבין למה אני רק מתקרב עם הזמן.
כן, כי זה פיקס פוינט מציבה.
כן, אבל אולי זה כבר מחוץ לבייסין of attraction.
לא, זה מה שאמרתי, שאתה יכול להניח שהבייסין of attraction מורכב
אוקיי, מכיל את זה.
בעצם כן, זה כל הרביע הזה.
אז אם אני מתחיל פה, אז אני אגיע שם.
כן. Let's go back to class. Okay, break is over. נו. Okay, so I have here a system with a saddle and an unstable fixed point. And the idea is to show this this homoclinic bifurcation. So this is the unstable fixed point, and I can see that trajectories spiral out of it. And this trajectory here, it approached the saddle, it was thrown away next to the unstable manifold, and then it came back next to the stable manifold and was thrown away again.
What are we looking at? What is it?
There is a saddle here. Draw some orbits to show that it's a saddle.
Can the orbits trajectories run a bit slower? Maybe different colors?
No.
Where is the saddle?
The saddle is at the origin. Okay? So you see things that can approach the saddle, but are then thrown away. Okay? Here, these are thrown away over this whole region and go along this unstable manifold. And this stable manifold of the saddle is actually coming from the unstable fixed point. There is one spiral that comes out of here that goes into the saddle. And spirals that are kind of, some spirals no, sorry, that was, so the spirals that go out of here, yeah, okay. The spirals that go out of the fixed point are thrown away here, and there is one trajectory that comes from here somewhere, and will go through. Let's see.
This system is an example of what?
This is an example for the homoclinic bifurcation. So this is a situation of this is a situation where there is no limit cycle. So things spiral out of here and are thrown away here. And the situation where there is a limit cycle, there's my mouse. Right. So here, there is a limit cycle around this unstable fixed point. If I started inside, if I started inside, I got to the limit cycle. If I started outside, I might converge to the limit cycle, or like I did now, or I might go around it. Okay. Yeah. So here we have a limit cycle around the unstable fixed point, but as I change mu, it grows. And here what we have is the homoclinic orbit. There should be one orbit that goes from here to here. All right.
But,
Yeah.
according to what you draw before, if it flows to the saddle and goes out and come back to the saddle, no?
It goes. Yeah. Wait a minute. with the homoclinic orbit, okay. So the homoclinic orbit should occur for only the bifurcation point, okay? And let's see if we can see it again.
It's not for mu greater than mu.
Say again. No. Okay, so the homoclinic orbit is a special case, and it occurs for the bifurcation point.
So
Okay.
you didn't
Yeah.
know what happened after that.
So, right. Um, okay, it's a little confusing, but this is what happens. So there is one spiral that goes into the saddle. Others should go outside through here. This unstable manifold also goes around this very special spiral and gets thrown away. And basically, everything goes to infinity from here.
So there's no limit cycle.
No, there was a limit cycle here at the bifurcation point. There was this trajectory, and then there was this. And here, in this case, the spiral will go into the saddle next to this. Actually, I'm sorry, I'm not sure what happens with the spiral. It won't route for now. Okay. So what happened here was this case of everything getting thrown away to infinity. Along one specific direction. But the same system with a different value for the bifurcation parameter gave a limit cycle that separates this from this. And the limit cycle disappeared through growing and annexing the saddle and becoming a homoclinic orbit of the saddle. Okay, so these were the bifurcations in 2 dimensions. And like I said, there's not much that we need to do with them except know them, except seeing what they're about. And there is no great way to treat them analytically, for example. Now we move on to the subject of 3D systems. Excuse me? Okay, this is just to have a whiteboard. Okay, so you remember that when we went from 1D to 2D, we got more complicated dynamics, and we got oscillations possible in spirals and in closed orbits and in limit cycles. So in the 3D systems, we add a dimension, and also we get new phenomena. And especially the possibility of chaotic behavior. You won't always get chaos. Okay, it's similar to what we had with bifurcations and limit cycles occurring for certain values of the parameters. Some nonlinear three-dimensional system will not be chaotic. Some will be chaotic. We'll see exactly what it means that they are chaotic. And specifically, we get the phenomenon of a strange attractor, which we'll see today, which adds to the possibilities that we had before of fixed points, limit cycles, closed orbits, and it's really something different. And as we begin to deal with chaos in 3D nonlinear systems, I want to stress that the word chaos implies nothing random or stochastic here. There is nothing unpredictable. Okay, if you know exactly the initial conditions, there is nothing unpredictable. So I think the term is a bit misleading, because we are dealing with deterministic systems. Okay, no stochastic noise, for example. But still, only because of the fact that we have 3 dimensions and the system is nonlinear, we get very complex behavior. Okay, and then add stochastic noise, and then you get things that are really unpredictable. But we won't do that, of course. We will stick to the deterministic system. Okay, so we will introduce the subject of chaos through the classical example of the Lorentz system. This is without a T. Lorentz. So Edward Lorentz was a scientist dealing with flows in the atmosphere, and he was working on a model of convection flows in the atmosphere. That's hot air going up and cold air going down, and he brought this to a simplified system. Now, while I write it, I want to mention that his discoveries were made possible by the fact that he had a computer. So he could do simulations of this system, and this gave a real boost to the subject of dynamics. Okay, so it's a 3-dimensional system where we have 3 parameters. R is the Rayleigh number. And okay, so B is a parameter. I don't remember if it has a meaning. I can check in a moment.
Meaning of the parameter?
I don't remember its physical meaning. So.
It's not about
No. Okay, b equals 1 plus a squared. If anyone really wants to know, you're welcome to remind me and I look for it. But in order not to waste time, I'll just mention that sigma and r are parameters of the fluid that is flowing here, specifically air. So, and notice that we have two nonlinear terms in the system. Okay? And the other things are linear. And in short, x, okay, so, the model here deals with the flow going up and the flow going down. So x is related to the intensity of these flows going up and down, and y is related to the difference between their temperatures, between the temperature of the air going up and the air going down, up and down. And z is it represents it characterizes the temperature gradient that you have. So basically, you would have maybe the sun heating air or the earth. I don't know, and so there will be a temperature gradient that causes this convection, and z is how much this temperature gradient is nonlinear. It's some measure of its nonlinearity. But we'll see that x and y basically behave similarly in our model, and z is a little special. Yeah. And the first thing I will do is I will show you the results of a simulation of this system.
What's the limitation of the parameters?
The limits on the parameters? I don't know. I don't know if they have limits. So what I'm doing is the same that Edward Lawrence did. It's just simulating the system. I guess it took him a lot more time. And yeah, still takes my computer a lot of time. In the meantime, we can look for the meaning of B. Okay, they have here alpha and A, and I'm not sure they're the same. Okay, it looks like B is related to the thermal expansion. Let's go back to MATLAB. Okay, so here I plot X, Y, and Z. Yeah. So we have these oscillations. So the convective flow is an oscillation, but it's it's kind of constantly occurring, this oscillation, and sometimes it's more, say, more fast, and sometimes it's slower, and sometimes it will change direction. And these parameters are in the phase space. They're already kind of the intensity, the temperature difference between the flows, and so on, and they are oscillating. And this behavior is non-periodic. Okay, Lawrence looked a lot for is there any order in this, but there is none apparently, and moreover, even when it seems, for example, maybe this part here is similar to this part here, and this part here is similar to this part here, the values are never exactly the same. You will never pass an x and y and z coordinate that you have already occupied.
Can never happen, or in this particular case?
So when the system settles to its stable behavior, then you never cross. Well, yeah, it can never happen because of the existence in uniqueness theorem. So, okay, unless okay, I'll get to it actually later. So what's important here is that there is no periodicity. It may look sometimes like there are periodic behaviors occurring, but it's never exactly the same.
But if you will stimulate again the same initial condition, you get exactly the same.
Yes, exactly the same initial conditions will give the same thing. Slightly different initial conditions will give very different things. Yeah. Time. Okay, I'll do it again. Okay, I'll just let it run. Okay, so this was very confusing, and the let's say the handle that Lawrence found on it was to plot things in phase space. Okay, looking at what happens versus time was not very relevant. Though later he did make something out of it. Oh. So I'm choosing here an initial condition on the x-y axis and some arbitrary z. It'll take some time again. Yeah, we need to wait.
So z doesn't change in this?
No, it changes. It's just an arbitrary initial value. Okay.
So it'll be 3d at the end?
Yeah. It's hard to choose a point in 3D in MATLAB. Okay. It says pause. I don't know. Okay, sorry for the sluggishness. Um, okay, so I chose some initial conditions, and you see that we have this period of that looks a little different, and then we will settle into the more stable behavior. And this is what it looks like in phase space, and it's a famous shape. It's this butterfly shape.
Can we see it in 3D?
Yeah, yeah, we'll see it. But let's use this. So I'm rotating it, and you see it looks like there are two lobes, two wings, and they're kind of not perpendicular, but they're not on the same plane. And each one is filled with these spirals. Okay. And the system basically, it maybe we can get a better view. Yeah. Okay, this is good. So the system basically, you see that, say here. No. Okay. So here, look, there is this trajectory. We cross into the second lobe, and here in the second lobe we will do a few cycles, and then cross back into the first lobe, and do a few cycles, and cross back into the first lobe. And this would go on forever and ever. Okay, never repeating, never crossing a trajectory, never intersecting a trajectory.
So if you would wait longer, everything would be blue inside?
Yeah, pretty much. Now, these lobes, maybe you saw them in profile, they looked flat, but they are not actually flat. If they were flat, we would have a problem of not intersecting ourselves and still filling up this space. So they're not actually flat, and this surface, this butterfly surface that we are on, it's almost a surface. It has a dimension of 2.05. Okay, so the lines occupy a surface, but they kind of jitter around the surface. It's not a two-dimensional surface. So they jitter around it, and this makes it possible to never repeat. Okay, so this type of behavior, this is not a limit cycle, right? We can wait forever, and there will be no real periodicity and no going back over our tracks. This is a strange attractor. It's one example of a strange attractor. And
it does have limits. I mean, in each x, y, and z, it cannot cross certain values.
Yes. So the strange attractor is a subset of the three-dimensional space. Okay, so Lorenz's discovery led to the definition of chaos. And so I will give some properties. Okay, back here. Okay, so our definition, write it in green. Our definition for chaos is aperiodic aperiodic long-term behavior.
Aperiodic infinite.
What?
Aperiodic final.
Final?
Infinite.
Yeah. Yeah, well, this was the definition that I found, so. Yeah, you're right. In a deterministic system, that exhibits sensitive dependence on initial conditions. And we'll see also something about this on initial. Can you see this green marker? What? No, because they want to show a few other things. But I'll try the other black one. That's okay. Okay, so aperiodic means it does not settle down to fixed points, limit cycles. Okay, general closed orbits. Or quasi-periodic orbits.
This is the definition for what exactly? Chaos.
For aperiodic behavior. This, everything?
Everything is
chaos. Okay. So it does not settle down. This doesn't mean that there are no fixed points in the system that we saw. 0, 0 is always a fixed point, the origin of the axis. And it doesn't mean that there are no limit cycles. Maybe there are unstable limit cycles. And if I'm not mistaken, if the initial conditions are too far away from the origin, then we don't settle into the strange attractor. We go to infinity. I'm not sure. But